Listo. Espérame tantito. A comenzar. En esta ocasión nos acompaña la doctora Nesrin MANAV.
My sister?
Yeah?
Yes.
Nesrin.
Nesrin. You can call me Nes, it's fine.
Nesrin MANAV, ella es profesora asistente de la Universidad de... Lo voy a leer como lo está escrito. Erzincan, Binali, Yildirim University, del Departamento de Matemáticas en Turquía. Ella es especialista de la propiedad del punto fijo. Hizo sus estudios de doctorado en la Universidad de Gazi, en Ankara, Turquía, en topología y obviamente en la propiedad del punto fijo, dentro del 2013 al 2019. Tiene, me parece que al menos 4 publicaciones sobre la propiedad del punto fijo. Ha tenido algunas estancias y algunos congresos, por ejemplo, en Dinamarca, en Texas, en Estados Unidos ha estado varias veces, en Irlanda, en Alemania, en España, en Italia, y una de las, pues no sé si de las cosas curiosas que ella tiene es que ha estado trabajando o ha trabajado en una estación de radio, en una estación de radio local, en donde se dedica a esta parte de difundir la ciencia y la tecnología. Y nada más como anécdota, a ella la conocimos Leonardo Juárez y yo, una vez que fuimos a un Summer Topology en Irlanda, y estábamos perdidos ahí en el centro de Galway, me parece, y ella nos ayudó y nos regresó, ya no íbamos de regreso y nos regresó otra vez al centro y volvimos a estar perdidos. Entonces, pues, así como que pensó que nos había ayudado mucho, pero en algún momento nos volvió a perder. Pero bueno, esa es una de las anécdotas que tengo, y fue ahí donde la conocimos, y desde entonces he tenido contacto con ella por medio de estas redes sociales. Nes, if you are ready, you can start.
Thank you so much. Thank you, Felix. You're inviting me this section today and introducing me very well, if I understand. So, hello, everyone. So, welcome my presentation. And here is the title. I'm starting right now. Some fixed point theorems in generalized modular metric space. It's what I work on nowadays. Oh, just a moment. I'm trying to understand, how I can, just visit another pages. I like to start with a story here. In the 1990, well, actually in the first 1950, Nakano, you can see on the footnote, gave the definition of a modular vector space. Then in 1990, those guys here, in 1990, some guys come up with a fixed point theory on modular function space. The modular function space is the special case of a modular vector space. This part is very important for us. Then 2010, guy, Chistiako, gave the definition of a modular metric space as we know today. And he had the motivation, but different than Abdu and Hamsi here, you can see. They, well, I like to, use the draw part here. Just a moment. So I think I can draw like this. Oh no, I couldn't. Okay, anyways. So my motivation is same with those guys. Yes, my motivation is same with those guys. Then, well, actually, then another work come up, and those guys here, Jalel and Samet, gave a new generalized modular metric space definition. Generalized metric space definition. It was the more generalized one for the metric spaces ever defined, but it didn't generalize modular metric space as they claim. We see the gap and we try, we fill the gap with the more useful definition. I'm going to show you here what they give us. First, if you see the definition of a function, is just like a normal metric definition, normal metric function definition. But the difference is including here the infinity part. Then they gave a set with the notation like this. Then the first two conditions never change. It's same like in a metric definition, but instead of a triangle inequality, they define this inequality, their inequality, and they say this is a generalized metric space. So then it was really easy to see how we apply this generalized definition for the other metric spaces. First of all, like an example, standard metric space. If we put C is equal to 1, our generalized metric space will be a standard metric space. Then if we put, maybe someone knows what is the B metric space. Oh, sorry. Okay, I put too much stress on my desk here. Okay. So if someone knows what is the B metric space, if we put rather than C is the S, so that it will be our metric space, B metric space, will be a generalized metric space again. So it covers those conditions. Then we talk about what is the modular space. Here is the modular vector space, and what gave the Kannan to as a definition. So the modular space has three, you can see conditions here. The first is same like a modular, like a metric space, pardon me. I used to say like a modular all the time, and it's just my tongue is never gives up. So, and the second definition is a little bit different for the third one. We have to be careful because the third one is very important while we're going to we are going to define the modular metric space. It's a base for us. And here is the most important part. While we collect alpha and beta, they will be equal to 1. So then, another very important property here we call Faro property. So for every x, and we are going to take some sequences. Any question? Okay, I heard something. Then if we put the limit like this, like xn converge to x on the function of rho of a function of a modular, then we're going to say the rho x will be less or equal to limit infimum rho o xn. So if we have a photo property in a modular space, we are going to talk about the third condition of a generalized metric space. So here it was little down, but you can see still, I guess, if we have a modular vector space, then we're going to define the generalized metric space, such as rho of x minus y, will be a generalized metric on x, y, but with the photo property. So here is how it works, how generalized metric works on another metrics, but not working on a modular metric space. First, I'd like to introduce what is modular metric space and why we need another definition for this type of a metric space. The story starts with lambda, and the lambda you can see on this set of values, including infinity, and it's very important. So we call it a modular metric or metric modular, as the Chesyakov said. It has three special properties for all lambda, and x is y is equal to y, while their distance on the modular is 0. Then they will be equal. I mean, if we change their place, but the third one, rather than a triangle inequality, the Chesyakov gave this definition for all lambda and mu. And this is the important part. This is the very important part for us. So some properties will surprise you if you get deeper how it works, how the triangle inequality is not satisfied in this space. It will be very nice for the mathematical exercise for some of us, maybe. Here is some examples to understand what is modular metric. I like to put some, special but very well-known metrics, like indiscrete metric. Here, if x and y is equal, we're going to say that the value of the omega lambda will be 0, and if they're different, the value will be infinite. Then if we have a usual metric d, and we're going to say if we have a here non-decreasing function, d over this 5 function going to give us another modular. So you will see y is not same like a metric. Then the third one is kind of another version of indiscrete metric. So here, just a moment, I really like to use my draw here, but I don't know why I'm not going to, well, if I use, yes, it's okay, I see. Okay, here is, like modular metric space has a history and story. And the story, they start with the motivation. We like to talk about the motivation here, modular metric space. Chesyakov gave us a physical interpretation of a modular metric, the average velocity. Average velocity between 2 points here, x and y. And we're going to divide the distance lambda, this distance with lambda here. So, and as we take lambda as a time, the omega lambda xy will be an average velocity for us. And it's, okay. I'm trying to get another, okay. Another page. Oh, yes. Here it is. Afra and Hamsi has a different approach. As we said earlier, they take modular metric space, not to finish, some like average velocity interpretation. They take it as a special case of a classical modular space, like a non-linear version, like as a non-linear version. and the modular function space defined by Michalak and Orlik. So here is, oh, okay, I should, yes, use eraser now, huh? Okay, so yes, here is our definition. We just put, the same first two conditions here. Well, I like to say it's our solution for the gap. And it's really important here. We didn't use all lambda. We just put some lambda, because if we take all lambda here for all the situations, and we are going to find many counter examples, they're not satisfying all those conditions. So here it is. We say, yes, we can put this here as a generalized situation, but for some lambda, but especially in a modular case, not a metric case. And our modular vector space, if we like to define as a generalized metric space, the first two conditions are, well, if we define the generalized modular metric as rho xy over lambda, we're going to find that if rho satisfies the photo property, then we have a sequence xn over lambda that rho converges to x over lambda. Then if it satisfies the photo property, then we will say, yes, it has it has a photo property. While it has a photo property, it will be it will satisfy the third condition of generalized modular metric. So, and the modular vector space is a generalized modular metric space. Then for the modular metric space, again, we're going to say, if we have a photo property again, then while we are using the photo property, we just say here for some lambda and for any y, it's going to imply that they are same in the generalized case. But we just gave some examples that they're not same, in other situations without photo property. Then let's look at how we gave fixed point theory and how it works on generalized modular. We're going to start with Banach, then we're going to give Kirch's fixed point theory, then Kannan and the Reich. So yeah, a little glimpse to some usual definitions as we know as mathematicians. Generalized type of the convergent sequence, then the Cauchy sequence, and then, as you know, what is the closed set if we have a subset of X, and what is the completeness here with the Cauchy sequence is, converges to 0. We're going to say it's the complete, and the boundedness is important here. We're going to give a new definition of a set, and we're going to define this with the delta with d, lambda, and c, and it's very important here. So okay, and here is this some B limits and its uniqueness. We have a lemma. If we have a generalized modular metric space and a sequence in it, then we're going to say, yes, it will converging is to a different a sequence, the converges to a different points. Well, they're not going to be different. with this third property of a generalized modular metric. So I hope I'm not going to, quick. So I like to be very quick. Here is the definition of a decontraction. Uniqueness of a fixed point theory if we have a contraction mapping function with its generalized proof with uniqueness. So the Banach said, well, gave us a, what is the contraction, and we're going to apply this definition to a generalized modular space. The contraction mapping we called F as a contraction mapping, while we say D1 of X, X of F, and pardon me, F of X and F of Y is less than equal K B1 of XY. So then we're going to say, yeah, maybe X is a fixed point while is satisfying F of X is equal to X. This is the regular, the standardized, very standard definition of a Banach contraction. Then we like to give more definition while we are going to use in the proof. So here is our lemma. And if we have a decontraction, we claim that we have just one fixed point in generalized modular metric space. And with its properties, it's obvious. If we have a decontraction and claiming that two fixed points, we have just their distance is not infinite. We'll say it might be 0, and if it's 0, they are equal points. So another useful definition is the orbit. The orbit of X is like this sequence with the F function. The mapping F is just gaining more power while it's getting continuous. So, and just I like to remind what was the distance in a usual set here. So then, yes, while we're trying to prove, the orbit definition will be very useful, and the supremum distance between the functions as well. So here is our theorem. From this theorem, we have the complete, the continuous mapping, and the set delta T1 x0 is finite, but for some x0, then we claim that the Fn x0 sequence is deconvergent to a point omega. And if it's x omega, the distance between x and omega with the generalized metric, modular metric, if it's infinite, then the sequence is deconverges to omega. So yeah, here is our Banach contraction principle and our fixed point theorem. So in the end of the Banach, we're going to visit the Kirk's fixed point theorem, and we are going to say what is Kirk saying about our fixed point theory here. So we are introducing right now what is the classic contraction. The classic contraction in generalized modular metric space has a definition such as with K, and K is from this interval, and we have some values for X, Y, above X and above Y. Then we're going to use this definition here, if we have a quasi-contraction mapping in our space, then we're going to prove it has a unique fixed point with this lemma. So if we claim that we have just only one fixed point, so the distance is not infinite, then we have a distance is 0. But if we claim that we have two different fixed points, then we need more, like the distance between them and the between the same points might be, well, not be infinite, might be finite. So then we claim that we have just only one fixed point. So in their original work, Jalal and Samet gave the following theorem about the Carrick fixed point theorem. So they said, yes, we have the complete generalized metric space, then we have the contraction mapping, then we have this set is not finite, well, it's finite, not infinite. So then we're going to say this function sequence deconverges, to a lambda, omega. So then we have just only one fixed point here. But those guys on the footnote, you're going to find a counterexample. Counterexample why it was not enough in generalized case. All the conditions of a theorem wasn't enough. Then here is our solution. We just did a little thing here, put a K with C, and while they're working together, and C is a constant from the third condition of a generalized modular metric, then we say, yes, we have a fixed point right now. Okay. Then I like to give the Kannan's approach, and the Kannan said, yeah, we have a generalized, if we have a generalized metric space, generalized modular metric space, then we're going to give this definition of the, well, inequality here. It's a definition as well, the lambda sequence of Kannan type. Then you can find the lambda sequence, and we're going to find the lambda here 1. So we're going to put, we are using the modular case as a regular here. Then the C from this interval. Then we say here, lambda sequence of a Kannan type, our xn, and it satisfies this equality, then we have these conditions and they are equivalent here. So it will be less than 1, the K of lambda n set, and the limit of this sequence will be 0 under the generalized modular metric conditions. And I like to give a little proof here. And I don't like to make you, oh, it's too much for me today, and I like to think about it more. I'm just going to pass this part a little quickly, maybe if you like to see, oh, okay. Just a moment, please. Yeah. And I love to send you the presentation. And we gave the definition of a Kannan contraction here. The Kannan contraction says if we have a mapping, we're going to take the distance of f of x and f of y with this condition, and it's similar to the Kannan condition. So we have a Kannan type sequence, and it's a Cauchy as well. Then for the sum lambda, this integer n work for us, such as this k of lambda n will be finite. Then it has a fixed point theorem. If those conditions are held and are well convergent, lambda is going to like the lambda from the k o lambda n is defined as d1 x over f of x. It's right continuous. We're going to say yes, we have a fixed point right now. And I put a little proof. If you like to check, again, I like to send you, really, I will be really happy. And if you ask me to send, and I put a little more maybe. So the definition, I mean, the proof part is kind of boring. So at least the Reich fixed point theorem is like that. First, the recontraction with a special, we have f still here, and we define mu function as, pardon me, as r, and the r has this property here. Then we're going to say yes, in our definition, which is all the values coming from 0 and 1 will be here is 0 and 1, is kind of like special type of Banach contraction. So we are going to say yes, then we have a fixed point. Then it's the fixed point theorem. It says D1 is convex and regular with delta 2 condition, and the delta 2 condition is similar to photo property. And I'd like to, open this subject more here. Then this non-empty subset we have, then we're going to say if we have a function as a Reich function, then f has a unique fixed point, and the sequence of f is converges the x star, and here is its proof. So if you like to check the proof, you will see we just use the Reich contraction and the orbits, as we mentioned before, and we define how it's going to work with the impeding. Then, and here it is at the end. I couldn't find more space and said it converges to 0, and it will be then Cauchy. So here is the end. Thank you for being patient, and thank you, Felix, for your introducing me and inviting me again. I will be very happy to see your questions. So I say stop share. Yes.
Any question, preguntas? David.
Aquí estoy.
¿Algo que quieras agregar, David?
No, creo que no.
So yeah,
There's no question.
Oh, really? Thank you. Thank you, patient, your patience. Thank you. And
I think that your presentation, your results are very interesting.
thank you so much.
Because I didn't know all the generalization of this concept. I saw that in your country it's very common to work in this topic. In the top on the fixed point.
Yeah, because it has many applications. It's very interesting for the people nowadays. Well, I found a thesis, and it was about electrological fluids and written in Germany. And well, I learned what is the story behind this thesis. And they try to understand how the electrological fluids behave, and they like to give the interpretation mathematically. But they didn't know how to do it. Then they start, work on this subject, and they are working on more applicable part of mathematics. So they found some people from Finland, and they asked, let's work on this, and they're working on analysis. And they, found in the end very interesting results mathematically. Then, well, the modular metric gave, pardon me, the modular metric case just, this more, I can say, theoretical part of this application. And it's very well suits with their results.
Okay.
And it's really interesting for me too.
Yeah. Thank you, Nes. For me, was a pleasure to see you, to listen, to hear this moment. Thank you for accepting to give this talk. For us, it's very important to have people of the other country.
Of my country as well. Yeah. I have some friends here.
Yeah. As soon as I can, I will send you the certificate for this.
Thank you so much. It's very kind of you. And very kind of your department as well.
Yeah, I don't know if somebody have some question, some comment, a selfie, a photograph, okay, or something like that.
Pardon me. Oh yeah, I like to share my presentation with any people who's asking, and if you like to send them, I will be very happy. If
yes,
they
can
ask
I share your presentation?
Yes, please. Yeah, okay. It will be real nice.
Okay. David, ¿algo más?
Estoy pensando, pero no, creo que no.
Okay. Thank you again. And see you soon.
See you soon. Have a wonderful day for the rest, everybody. Thank you so much again.
Thank you.
Thank you.